This is problem 15.6. It's on page 664. A small grinding wheel is attached to the shaft of an electric motor which has a rated speed of 3600 RPM. When the power is turned on, the unit reaches its rated speed in 5 seconds. When the power is turned off, the unit coasts to rest in 70 seconds. Assuming uniformly accelerated motion, determine the number of revolutions that the motor executes, A, in reaching its rated speed, and B, in coasting to rest. Okay, let's see. We've got that the rated speed is 3,600 revolutions per minute. If you multiply that by 2 pi radians per revolution and by 1 minute per 60 seconds, you'll find that that is a speed of about 376.9911. I don't know why I kept so many decimal places. Radians per second. Now the amount of time that it takes for starting is 5 seconds, and the amount of time required to stop is 70 seconds. Now we're supposed to assume uniform acceleration. That means that the acceleration is constant. In this case we're talking about angular acceleration, not linear acceleration, so it's alpha that's constant, not an A. We're supposed to find the number of revolutions during startup and the number of revolutions during stopping. So what we'll have to do is use the constant acceleration equations we have, and whichever one is most useful is the one we should use. Now what were we given here? I wrote this down as an N on purpose. Well, usually we use N when rotational speed is given in revolutions per minute, but once it's changed into radians per second, we usually give it the symbol omega. So this is the angular speed omega in radians per second of the shaft. Now if it takes 5 seconds to start up, then we'd like to know the number of revolutions. So let's figure it out. Let's start off with this equation. The angular speed is the initial angular speed plus the angular acceleration times the amount of time that it takes for it to accelerate. That way we can calculate the angular acceleration. It's just omega less omega naught over t. Now once we know the angular acceleration, then we can talk about the change in angular position from the initial position via this equation. Okay, so the first equation is the constant acceleration equation for angular speed. The second equation is the constant angular the constant angular acceleration equation for position. And so what I'll do is I'll find the angular acceleration from the first equation, plug it into the second, plug the time into the second as well, and then be able to find the angular position change. In fact, we could write down the angular position change, theta less theta naught, as initial speed t plus 1/2, and instead of alpha, if I just write omega less omega naught over t times t squared, you see we can simplify this down a bit. Omega naught, now in the first case, the initial speed is 0, but we won't cross that off quite yet. So let's see, omega naught t plus 1/2. Now what do we have? T squared over t, well that's just t. So omega t minus 1/2 omega naught t. So we end up with an equation, let's see, take half away, it would just be 1/2 t, factoring out the t and the half, putting these two together first, of course, so that we get a positive remainder here of half omega naught t, and then this would be omega naught plus omega. Okay, so the change in position is then given by this equation. Now for part A, we know that the initial speed is 0, and so the change in angular position, or the number of revolutions, in this case radians, is going to be 1/2 t, but t is 5 seconds, multiplied by omega naught, which is 0, plus the speed, which is 376.911 radians per second. Now, of course, no, we don't have to put the angular speed in radians per second. We could have simply gone back and put in 3,600 revolutions per minute, converting that to seconds so that we have consistent second units. 3,600 divided by 60 would be 60, right? So this is 60 revolutions per second. So I didn't have to plug it in that way. I could have plugged in 60 revolutions per second. The seconds would go away and we would just have revolutions. You can do this math in your head. Delta theta then, or the number of turns for part A, would be 60 over 2, which is 30. 30 times 5, well, that's 150. So 150 revolutions is the answer for part A. How about part B? Well, for part B, it's the final speed, omega, that is 0, because remember, the initial speed is 1500 RPM. Now, the equation's the exact same. Notice all I've done here is use constant acceleration equations, which is true for part A and part B. We have constant acceleration in both those cases. What's different is that now the initial speed is the 1500 RPM. I keep saying that, I'm quoting the wrong number. It's 3600 RPM. Let me make sure that's right in the statement. Yeah, 3600, I'm sorry. I think I've said 1500 a couple times. I don't know where I got that from. So 3600 RPM is the initial speed, but now there is no final speed and the time is 70 seconds. So basically, delta theta, again from this equation right here, is 1/2, now we have 70 seconds. Omega naught is 60 revolutions per second. Notice I'm using 3,600 revolutions per minute, converted to revolutions per second, so it goes, so the time unit's going to go away. And then plus, pardon me, the final velocity. Now the final velocity is 0. Okay, so doing this math, we take 30 times 70, and if you did that, you'd find that that is 2,100 revolutions. So there's our answer for part A and part B. 150 revolutions is how many turns it takes before the motor's up to the operating speed and the motor slows down in 2,100 revolutions and comes to a stop.